presumably want to get a better job when you finish school. So luckily I'm here to help you with some real marketable skills rather than just, some of the theoretical nonsense that you get in math classes. This is some really useful hands-on stuff. So what are you going to do to make money when you finish this class? Well, of course, you're going to make artisanal beach balls. That's just the only thing that makes sense. People love artisanal stuff. Then they also like to go to the beach and play with beach balls. So what we're going to do is we're going to learn how to make artisanal beach balls. So what do? Well, you have your beach ball, and it's got to be artisanal. So you're going to sew it. And maybe you might not know much about sewing, but luckily I basically invented sewing. I mean, not exactly, not technically, but more or less. The way that sewing works is you're going to put some buttons on the ball, and then you'll use those to make seams, and connecting those buttons by seams, and those seams are going to form the boundaries of various flaps. Okay, and maybe one of the principal things that you're going to need to learn is that well, first off, you're not going to be able to just sew a perfect sphere. Because it's artisanal. If it's all like perfect, then people are like, oh, this doesn't look very artisanal. This looks like it was made by a machine. And you're like, oh, okay, now I can't eat because you won't give me money. So what you're gonna do is you're gonna sew it with at least one button. And some of you might know that my wife is from Mexico, so we speak a lot of Spanish in the home. So to count the number of buttons, I'm going to use the letter V, because V and B make really similar sounds in Spanish. So V is going to be the number of buttons, and the size of so V is the set of buttons. Size of V is the number of buttons. E is going to be the number of seams. So this E for seam. I can't think of a better letter. And finally, we're going to have F, which is going to be for the number of flaps. Okay? So one thing that you're going to notice pretty quickly, that as soon as you have at least one button, we have that the number of buttons plus the number of flaps is equal to the number of seams plus 2. And we can prove this pretty quickly. The way we're going to prove this is by induction. Let's start with having just the one button. So we check. So for one button, well, that's easy. It's there's one button, one flap. And there are no seams. 1 plus 1 equals 0 plus 2. So we're good there. All right, now let's show that if I've done this for some number of seams, then and this is, sorry, V equals 1, this is when E equals 0, right? I can't just put seams on there without buttons, because that's not how sewing works. So this should be E equals 0 is what I really wanted to put here. V will equal 1 because you're going to need one button. But so E is equal to 0. Now let's take E, and let's show that this being true for E implies that it's true for the size of E plus 1. And the way to see this is if I add a seam, I add either a button or a flap. And what do I mean by that? Well, if I'm going to add a seam, I've either got to add another button out here, or I take one of my previous flaps and have to cut it in half. Okay, so we've just shown by induction that for any artisanal beach ball, we have that with at least one button, because otherwise it wouldn't be artisanal, it would be stupid. We're going to have that V plus F equals E plus 2. All right, well, that was really fun. Next, I want to show you something about artisanal beach balls. And that is if I let's go back to this artisanal beach ball here. Another theorem. So that was theorem 1. Let's call this theorem 2. That as long as I have at least 2 seams, then 3 times the number of flaps is less than or equal to 2 times the number of seams. And how do I know this? I'll let you think about that while I drink my Earl Grey tea, decaf Earl Grey tea with vanilla almond milk. This is essentially a crime that this even exists. Can you all see that? I don't know if you can see that. It's probably too dangerous for me to dump it on my laptop. Man, why would I waste time and talk about my tea? Oh, is this a math equation? Me plus wiener dogs equals love. Ah. Wiener dogs, right? Wiener dogs. Wait a minute. Wiener dogs, of course. If I view each seam as a wiener dog, see, I'm looking down at the wiener dog from above. Here's his 2 little ears. The wiener dogs like to sniff each other's snouts and each other's tails. So now I can count the number of wiener dog ears. And in fact, each wiener dog is a normal 2-eared wiener dog. So the number of wiener dog ears equals 2 times the number of seams. And I noticed that each flap, to be properly formed, must have at least 3 ears on it. Look, 1, 2, 3 on that triangular flap. 1, 2, 3, 4 on that sort of square flap. Then the outer flap, 1, 2, 3, 4, 5, 6, 7. It's definitely got at least 3. So each flap has at least 3 ears, meaning the number of dog ears is bounded below by 3 times the number of flaps. Hey, cool. We just proved that. That's a nice thing to prove about artisanal beach balls. Let's collect what we know. Theorem 1. If I have at least 1 button, then that means the number of buttons plus the number of flaps is equal to the number of seams plus 2. Theorem 2. If I have at least 2 seams, then I have that 3 times the number of flaps is less than or equal to 2 times the number of seams. Now, if this condition here seems a little artificial, it's because, beach balls with fewer seams, they exist. They're just not as cool. Okay? And we can prove something similar for beach balls with fewer seams, but we're going to go on ahead and not do that right away. If you are interested in learning more about this, email me. I can give you some literature on the subject. But we're just going to deal with this. Well, since this is a math class, we know that 1 plus 2 equals 3, right? So theorem 1 plus theorem 2 should give rise to theorem 3. Well, what is theorem 3? Let's prove theorem 3 and then we'll state it. Sometimes this is how math works. Well, by theorem 1, that tells me the number of flaps is equal to E minus V plus 2. Cool. Well, the number of flaps is somewhere in theorem 2, so by theorem 2, I just plug in for F here. I know that 3 times the quantity, E minus V plus 2, is bounded above by 2 times E. Let's do some arithmetic. I'm going to subtract 2E from both sides, so I have 3E minus 2E, and I have E, minus 3V, plus, and then 3 times the negative V gives me negative 3V, 3 times 2 gives me plus 6, and I've subtracted this off. And this tells me, that's where I want to stop, that if I have at least 2 seams on my artisanal beach ball, then I have that E minus 3V plus 6 is bounded above by 0. That means that this quantity is non-positive. Well, that's nice, isn't it? That's really nice. Okay, Well, now that I've given you some sort of like useful life skills in the last 10 minutes, let me go to something that you'll probably never ever hear about again, which is just something I'm going to kind of ramble on about for a while. Especially, in computer science, you'll probably never hear about this. We're going to talk about graphs. A graph, I'm going to say graph G, is a pair of sets, V and E, where the elements of V are called vertices, the elements of E are two-element subsets of V called edges. Now, by this definition, and using the naive definition of set that we have that a graph is this pair of sets where V is a set of elements called vertices, and E is a set of two-element subsets of V, meaning that my edges, my two-element subsets of V, are going to need two distinct elements of the vertex set. So the singular of vertices is vertex. Now, let's define some things about these. So we oftentimes, when we're dealing with graphs, we like to visualize them. So what I want to do now is I want to kind of chill you. I want to give you chills. I want to make you sort of frightened at my artistic ability. I mean, you remember the pigeons, right? You cried at the pigeons. This just might rupture your soul. What is that? Can you smell it? You can smell it. It's pizza. It's pizza, isn't it? You want to eat it. No, it's not. Don't eat it. It's a drawing of pizza. That's not actually pizza. That's a drawing of pizza. That was close. You almost started eating your computer screen and or phone. Okay, that is a drawing of pizza. So one way to communicate the idea of pizza is by giving someone a drawing of pizza. And then people are like, oh, yeah, I like to eat that. No, you don't like to eat the drawing. You like to eat, what's in the box with the drawing on it. Okay, so, or maybe, shoot, I don't know. Maybe you do like to eat drawings of pizza. Please don't eat the computer, though. Okay, so what we're going to do is we're going to sometimes represent graphs with drawings of graphs. So I could represent the graph here. This is an example. G has V equal to A, B, C, and E equal to the set containing A and B, and the set containing B and C. You notice this is a drawing of the graph, but this is not the graph. The graph is a pair of sets. Okay? Now, we can visualize that pair of sets using, we draw some points for the vertices. We connect those points by, let's say, C1 piecewise continuous curves or lines or whatever. But this is a drawing of the graph. The actual graph is a pair of sets. All right. Now I'm gonna skip through some things. If you want to learn more about graphs, I can email you more details. But let's just kind of take rigor a little bit lightly here, and I'm going to say a graph is connected if it's connected. That's a garbage definition. That's not really even a definition, okay? But suppose that my graph looks like this. We can imagine sort of traveling from this vertex to this vertex, right? So I would say this graph is connected. I would say this graph over here is not connected because no matter how I travel, from this vertex, I can never get to say this vertex. All right. There is a way to make this more precise. I don't want to do it for this class. Again, if you'd like to know more, shoot me an email. I'm also going to say a graph is called planar if it can be drawn with no edges crossing. An emphasis on can be drawn. So let's look at this graph here. I've drawn this graph with two edges crossing, but you notice that I could draw this graph without edges crossing. Remember, I've been using straight lines, but I said you don't actually have to have straight lines. I said, I think what I said was C1 piecewise continuous. So, you know, whatever, you can use your fancy words, but essentially this graph exhibits the same connections as this graph, but this one does it without crossings. So now, let's think about this graph. This is called the complete graph on 5 vertices. The one that I just erased was the complete graph on 4 vertices. I've got every possible edge shown. Can this graph be drawn without a crossing? Well, let's try. So I'm going to draw a pentagon, and I'll try to connect every pair of vertices, and I can get pretty far, but then eventually I've got 2 vertices that are not connected. The only way that I can connect them is by making a crossing. At least that's what it would seem like. So it turns out that one way to prove this quickly, it turns out, is to refer back to our artisanal beach balls. You'll recall in our artisanal beach balls, we proved that E minus 3V plus 6 was less than or equal to 0. Now, I haven't exactly told you how the artisanal beach ball is related to a graph, but I bet if you play around with some of the associated letters, you can kind of figure it out. So you notice that I couldn't make a beach ball with this on it because I'd need to add buttons where those edges cross, right? In fact, this graph is not well defined. The beach ball associated to this graph would not be well defined because I couldn't make the flaps work out, right? I'd need to add additional buttons, but then I would have more seams and more buttons, and it would be a different graph. It would be a different beach ball. So let's check how this inequality would apply here. Well, the number of edges, I've got 5 vertices, and every pair of them is an edge, so it's 5 choose 2, minus 3 times, well, the number of vertices is 5, plus 6. 5 choose 2, that's 5 factorial over 2 factorial, 3 factorial, minus 3 times 5 is 15, plus 6. Now 5 factorial over 3 factorial, 2 factorial, well, that'll be 5 times 4 over 2. This is 10 minus 15 plus 6. And 10 minus 15 plus 6 equals 1, and 1 is not less than or equal to 0, which means this cannot be a beach ball. And what that means is no matter how I draw this graph, there will be a crossing. Right now you're probably thinking, wonderful, Steve. Wonderful. What does all of this have to do with the reason that I'm watching this video? And the reason that I'm watching this video is, of course, to deal with the 5 farmers. The 5 farmers can be related to a graph, but probably not in the first way that you'd think. Let's look at 3 farmers. When we look at 3 farmers, what do we actually need? We need farmer 1 to have a house. We need farmer 2 to have a house, or, child 1, child 2, and we need child 3 to have a house. Then connecting these houses, I'm going to make a thin sidewalk with a very short length of fence on it. Okay? Now, this very short length of fence can be widened, and these sidewalks can be widened. And these sidewalks can be further widened, and the lengths of fence can be further widened until what I have resembles the diagram from before. Now, this diagram from before is probably not, when we were doing the problem before, you probably didn't think of it in this way, but this certainly works, right? So let's try to take the solution we have for 4 farmers, or 4 children, and make the corresponding house diagram. Well, I'd need a house for 1. Does the house have to look like that? It doesn't have to look like that. House for 2, a house for 3, and a house for 4. And then what do I need? I need to make sure that I can draw these sidewalks in. Well, here's a sidewalk, here's a sidewalk, here's a sidewalk, and this is starting to look like a flux capacitor. The resemblance is totally unintentional. Okay, now as I widen these sidewalks and widen these lengths of fence, what does this begin to resemble? As I widen these sidewalks, I end up with fence all around 4. That fence extends between 1 and 3, and this diagram becomes this diagram. But this diagram was born out of 1, 2, 4, and 3 being drawn as a graph. Oh dear, that's incorrect. Being drawn as a graph between 4 vertices with edges not crossing. So let's try to draw a graph on 5 vertices with edges not crossing. And presumably, if we could do this, we could put thin sidewalks with short lengths of fence on them, and then expand these out to make a proper diagram, right? Well, I need 1 to have a sidewalk to 3, but look at this. I need 2 to somehow have a sidewalk to 4, and I can't do it. As I expand this out, what do I get? Well, I've got 2 up here, I've got 1 up here, I've got 5 in the middle here, I've got 4 down here, 3 takes this space, we have 1's region wrap around and touch 3, and no matter what we do, 2 can never touch 4. And this is because I can't draw this graph without a crossing. So what I would suggest you do is first you try to watch this whole video again, because it has, let's just say, some potential to be confusing. Second, I would like for you to write down in words how the fact that this graph has a crossing means that we can't satisfy the farmers once they have 5 children, once they want to break up the land into 5 single contiguous pieces that all border one another in the length of fence. Thanks so much.